Welcome everybody to the final E240 lecture for this semester. So just one sort of administrative thing before we get going, actually maybe a couple. So obviously the project will be due on Monday, which is a fairly short number of days from now. So hopefully people are well on their way on that one. The presentations again will be on 9:30 on Monday, and they'll be at BWRC, so everyone needs to be there for that. The only other maybe logistical thing we need to do from a scheduling standpoint is that I will be holding a sort of review session where I'll just show up and sort of answer any questions that people have on the final itself. We'll probably do that on Tuesday, and maybe just to throw out a time, and for those who are here, they can sort of take a vote or a poll on it. So I was thinking of maybe doing it Tuesday at like 1 o'clock. So any objections or agreements with that? Everyone here can make it? And since you guys are here, you get to dominate the discussion, I guess. Okay, so let's go ahead and plan for that. So I'll post a note up on this on Piazza as well, but for those watching this on the video, we'll do the final review session on Tuesday, 1 p.m. I'll check on the exact room, but it'll probably be either here or in 550 Corey. Okay, and then of course the final will be on Wednesday at 11 a.m. I forget the exact room, but I'll also post that up, and I believe it's posted in the sort of regular final schedule as well. Is it 11 or 11:30? Okay, maybe it's 11:30. I'll go back and double check. Don't take anything I say here as set in stone. I'll post an announcement on Piazza, just double check. But maybe indeed it is actually 11:30. Okay, so any questions on either logistic stuff or material that we've been talking about so far? Or on the project, for that matter? Anybody actually finished the project already? No. Okay. 50% of the way through? Wow, it's going to be a busy few days. All right. Well, so if there's no questions or anything on that, material-wise, last time we were talking about MOS sample and hold circuits. And we were basically sort of walking through all of the different ways in which these real transistor-based sampling circuits are essentially non-ideal. So we had talked about things like finite bandwidth. We talked about things like distortion. And what we're basically getting into, or really actually sort of finishing up in some sense now, was charge injection. And we said that the thing that was really kind of nasty about charge injection was that, unfortunately, SPICE doesn't really model it very correctly. Because in order to model it correctly, it would actually have to use essentially a distributed model of the actual channel resistance and capacitance. And obviously that's not something you'd really like to do from the standpoint of getting any kind of reasonable run times in your simulation. So if you really want to get sort of a reasonably accurate answer to these things, you will typically have to do some kind of your own either hand analysis or MATLAB model or something like this in the very specific circuit that you're working in. So what SPICE actually does is it basically uses this X-part parameter to just decide what fraction of the channel charge actually goes either into the drain or to the source. And depending upon how you've set this parameter, it'll sort of just change the relative ratios of that charge injection. Which, again, this is totally bogus in the sense of the actual percentages here would really depend upon how the rest of the circuit is connected into your transistor. So again, user beware here, because you have to really carefully think about what would actually be the worst case for whatever particular scenario it is that you're interested in. So having said all that, as you can imagine, it'd be really nice if we could just get rid of that charge injection error completely, right? So we just, from a circuit standpoint, didn't really have to worry about how accurately it was actually being modeled. And so the good news is there are actually a couple of fairly simple tricks we can play to do that. So just as a reminder, let's again sort of draw our standard, sampling circuit there. So we just have some input voltage that we're trying to sample, our sampling switch, a clock, and then a capacitor, and of course this is our sampled voltage right here. Okay, so just as a reminder, if we looked at sort of what happened right after we turned off the clock edge, or really what voltage we sample onto that capacitor, then basically what we should get is that the output voltage should just be the input voltage. But then because of this charge injection error, there's going to be essentially some offset, right? Where that offset is really just related to the fixed charge that's always in the channel and totally independent of the input signal, right? So you can imagine if I'm applying sort of VDD of gate voltage there, then there's always something that's kind of related to VDD that's going to be coming out in terms of the charge injection. Now, there's also, of course, going to be a component that's actually related to the input signal. Okay, so I'm not going to make any statements about what the exact functional form of that is, although it's actually fairly straightforward to figure that out. But there's going to be some amount of sort of voltage at the output. That's, again, some function of some, let's say, nonlinear, or let's say some other function of the input. Okay, and I'm just going to call that f of v in. So the first question that I might ask you guys is there anything we can do to at least get rid of the offset term so that we can get rid of that so-called pedestal error where, we said that typically in this kind of scenario, the output would always be lower than what the input was. And in this case, by some fixed amount. Yeah, exactly. If you just do a differential sampling, okay, so we have, let's say, a Vn plus and a Vn minus. And for all intents and purposes, we just have the same circuit, but just repeat it twice for the two differential sides of the signal. So, of course, this would be V out plus and V out minus. If we look at our differential output, then, of course, what you'll get is just V in. And then because the offsets are common between the two of them, that will just fall out. Right? In other words, this will become a common mode signal. And then plus, actually, it'll be some other function of V in. And the reason, of course, this is some other function of V in is because this other function will be f of V in plus minus f of V in minus, which, depending upon what that function actually is, will have some other sort of form associated with it. Okay? Does this make sense to everybody? Or? All right, so this is good. We got rid of at least the offset. But we still are going to have this sort of potentially nonlinear or other input signal dependent term at the output. And in many cases, again, it would be really nice if we could get rid of this because this can fairly easily cause pretty large errors in our actual sampled outputs. So conceptually, at least, can anybody think of a way of making this term, quote unquote, go to 0 or at least be a constant? And by the way, this is a little bit of a trick question, so, if you think the answer is stupid, this may actually be the answer I'm looking for. So how do I make this term be a constant? Yeah, exactly. I have to make V in be constant. Okay, so now this may sound like a stupid idea, and at first it will be, but trust me, we're actually going to use exactly that idea. Okay? So the way we're going to use that idea is so-called bottom plate sampling. And the way it works is as follows. So I've now taken my sort of sampling circuit, and I still have this input switch much like I did before. But now, instead of sort of taking the output here, notice I'm actually taking the output sort of on the other side of the capacitor, A. And B, I have this extra sampling switch here, or this extra, let's just call it a switch for now, on this side. So the idea here is very simple. So if I look at this switch, because one side is ground, I basically know that the source of that transistor, at least when it's on, is always that ground. So in other words, when the transistor is on, its VGS should always be set by VDD. In other words, it's a constant. Well, so that means that if I turn this, when I want to actually do the sampling, if I turn this switch off first and still leave this switch on, well, notice the VGS is totally fixed. And so the charge in the channel should also be fixed. And so whatever charge I inject, whether it goes this way or that way, should be just a fixed amount of charge, right? Totally independent of the signal. And by the way, you should imagine also doing this in the differential configuration so that any fixed charge just becomes, a common mode variation in the output. Okay, so if I first, again, turn off that switch, then it will indeed inject some charge, but it'll be fixed charge. Now, the next trick I'm going to play is that when I really do want to do the final sampling, as we said, first I turn that switch off, then I'm going to turn this switch off. Now, the reason that this actually works, because, by the way, notice, of course, this switch, its VGS depends upon the input, right? It is going to be input dependent. But because I've already turned this switch off, ideally speaking at least, there's really no path for current to flow in this direction. Right? If this is really an open circuit, then no charge can actually go there. Right? So if I've really done this right, then when I turn this switch off, all of its charge will actually flow back to the input. In other words, it will not impact the sampled voltage at the output. Now again, this is of course somewhat idealized because I have to have no parasitic capacitance from the switch. I have no parasitic capacitance anywhere else on that node. But the idea nonetheless is a good one in the sense of by doing this, I can really minimize the amount of charge that will actually flow into my sampling capacitor. Now there's only one, let's say, minor caveat or minor issue here, which is the output voltage over here, of course, is totally independent of the input. It's always just 0, right? Because what do I do every cycle? I just turn the switch on, I make it 0 volts, and then I let go of the input, and if I just look at this voltage relative to ground, I always get 0, right? That doesn't seem particularly useful. Does this make sense to people, or? So by the way, if I actually do want to use this for something useful, how do I do that? What voltage do I actually have to measure, as opposed to V out relative to ground here? And I'll remind you, all voltages are relative. Yeah, exactly. You actually want to measure the voltage across C2. So I claim that actually we've seen many ways to do exactly that already. And if you actually look at the way we were building our sort of typical switch cap amplifier, if we did it the right way, we can actually do this exactly bottom plate sampling type of procedure. So let's see how we would do that. So if you remember our sort of classical switch cap amplifier, we were going to have an input capacitor that was going to be connected, of course, to Vin. And this time around, by the way, as we had done in the earlier picture, I'm actually going to separate the clock phases of that input switch and the grounding switch on the other side. Okay, then, of course, I'm going to have these extra switches that I'll be using in the second phase of operation. And by the way, don't worry, I'll draw sort of the full circuit in the different phases, meaning ignoring the switches in 1 second. And this, of course, will be our OTA with a capacitive feedback, which, I'm sorry, let me draw that more carefully. Should actually be a switch, of course, at the output right here, which will be in phi 1. Okay, so the idea here is, in the first phase of operation, just like before, I'll be sampling Vin across the input cap, and then essentially just resetting the output of the OTA. Okay? Then, in phase 2, or really much like in this previous picture, I'll essentially use my bottom plate sampling operation on this input cap, meaning I'll first let go of this switch, or turn this switch off. Then I will turn this switch off. And only then will I turn these two on to actually connect the amplifier in the sort of standard configuration that we've had it connected before, which of course is just something like this. So notice by doing this, what I'm really doing is I'm making sure that by controlling the timing here, I should not have any charge injection messing up the voltage that's actually across this capacitor here, or really the charge that's on that capacitor there. And then I just use that charge in my sort of standard feedback configuration to create a new output voltage that I'm interested in. Does this make sense to everybody? Or? So of course, I drew this all single-ended. You can actually do it differentially. And in fact, that's kind of what this picture here is indicating. It's just an example of sort of a differential version of the bottom plate sampling technique. The only thing that I'm sort of calling out here that's a little bit maybe different is that, as we had discussed in the past in the context of these comparators, right, you may not just want to actually short the input to some, or rather the other side of the sampling cap to some, let's say, known potential. In this case, I'm using the common mode. In the previous example, I was just showing it as ground, but for differential, common mode is the same as ground. You will also want a switch that's kind of connected across the inputs like this. Now again, the very specific thing we have to be careful of here is, if we're actually going to try and simulate this thing in SPICE and get the right answer, if you just go and sort of exactly plug the circuit in exactly the way I've drawn here, you might get some, let's say, unreasonable answers out of it. So in particular, and this is where I'll sort of give you a reminder about this x part stuff, let's say that I set x part to be equal to 1. Okay, so I have 100% charge injection just onto the drain of the transistor. And as a reminder, the drain is purely defined by which terminal you actually entered into the schematic as being this first one in the netlist. So if I just instantiated a transistor as I've drawn there in kind of the red across these two terminals here, what's the problem that I'm going to probably see that may not actually, in fact, is most likely completely bogus? What are you going to see happening there in your SPICE simulation?
All the charge is going to be injected to the 143.
Yeah, exactly. All the charge is going to go either this way or that way, even though, of course, in this case, that's totally bogus, right? There's no particular reason why that thing should behave that way. So the thing to be careful of there, or rather, particularly in the simulation, how you're going to want to sort of connect things to make sure this doesn't happen. And in fact, even in the real layout, if there's any chance that you have some asymmetry, then the sort of classic trick to play is to do something like the following. So if this is how the switch, let's say, originally was going to be configured, and we said that may have the asymmetry problem, well, if you want to fix it, then basically take the same exact switch, or really split the switch into two pieces, but then just flip the connection of the source and the drain. So in other words, I'll take that side and connect it to here, and take this side and connect it to there. Right? This is a lot like the sort of, I said way back when that you'd always want to have at least 2 fingers in each of your transistors to make the current flow directions sort of, have one always in one way, the other one always the other way. Very similar idea here. Right? So this is just a way of sort of ensuring that your bridging switch is symmetric by just taking something that initially was perhaps asymmetric, but then just flipping the connections to make sure that the overall thing is actually symmetric. Make sense to everybody, or? So, any last questions on sampling circuits and charge injection and things like that, or should we move on? All right, looks like there's no further questions. Let's go ahead and actually move on to the sort of final set of lecture notes, which, as I had mentioned last time, what I wanted to briefly do today was give you a little bit of an introduction into what the circuits that you would actually, if you actually wanted to build some of the equalizers that we talked about, back a few lectures ago, what would those circuits actually look like? What would be sort of the real circuit implementations? So before we sort of dive into a ton of detail there, I did want to sort of give you a little bit, first, of course, just a reminder what this equalization stuff was all about. But second, kind of give you a little bit of an idea as to what are some of the options you have in terms of doing that, building that equalization, as well as what some of the limitations really are. Okay? So first, just as a reminder, what we basically said was that, and of course you guys are seeing this in your project, if we look at some generic link, we have a transmitter, we have some channel or some set of transmission lines we're going over, and then we have a receiver. Well, of course, as a reminder, we said that for better or for worse, this channel never is really perfect. In other words, it always has some filtering effects, H of S, associated with it. And in particular, that H of S tends to be low pass in nature. Right, so if we draw the magnitude response, it tends to do, I'm drawing something drastically oversimplified, but, it does something like this. Maybe it actually has some reflections that, cause notches and things like that. But bottom line, it almost always looks some kind of low pass in nature. So that basically means that if we want to build an equalizer, which is really just trying to do the inverse filtering of the channel itself, then that effectively means we need to figure out how to build essentially some sort of a high-pass filter. Okay? Or at least a band-pass filter. Meaning you're going to try and make the low-frequency components have less gain than the high-frequency components. So, well, how can we do that? Well, there's a couple of different ways. One, which is maybe, let's say, the more traditional communication sort of view of the world. So you can say, well, I can take my digital data, I can pass it through some kind of FIR, or in fact maybe even IIR filter, where this FIR filter just creates some high frequency peaked type of response, and then feed that into a digital to analog converter. Okay, that's the sort of, let's say, the nicely partitioned of, I have a bunch of signal processing, and then I just convert it into the analog domain. Okay, that's one way you can build this equalization. The other way, and by the way, these are not necessarily mutually exclusive, is on the receive side, you can essentially build some analog circuit that has exactly the high-pass type of behavior we're interested in. And then, of course, feed that into your comparator or your set of comparators, as the case may be. Now, I guess maybe first questions first. What do you think I'm going to focus on in the rest of the lecture today? It should be obvious, so I just need somebody to actually say it. Yeah, okay, the analog one. Now, other than just this is an analog class and maybe I like analog stuff, why am I going to focus on that one? What's let's say, a technical reason for doing that? Okay, you said you can't afford to. When you say can't afford, specifically, what's the sort of problem? Like, can't afford from what standpoint? Okay, so power and area. Now, I think that is actually correct, but really just as a reminder, why is it that sort of doing stuff on the transmitter tends to be more expensive than doing stuff on the receiver? What's different about the two? Oh, you said larger signal swing. That is potentially true, although not necessarily, but there's something that's, let's say, perhaps related to that. There we go. It's impedance. Okay, so as we had talked about earlier in terms of even just from a swing standpoint, or let's say swing versus gain, on the transmitter, sorry, you have to drive that 50 ohm termination, plus, of course, the transmission line itself, which generally means that output node is driving something like a 25 ohm impedance. On the receive side, well, I'm just driving the capacitance of my comparator or whatever other stages there are in my circuit. And even at very high frequencies, unless you have some pretty big capacitors, the impedance tends to be much higher than that 25 ohms on the transmitter. And so because of that, oftentimes doing stuff on the receiver does become actually more efficient, so to speak. Meaning for the same sort of function that you're doing, it costs you less power to actually implement it. All right, so now there's another sort of interesting point to keep in mind here, which is, as we had said way back when, if I wanted to build an equalizer to sort of cancel out the low frequency filter, or rather the low pass nature of the channel, that generally means that you're going to have to build something that sort of looks like this from a frequency domain standpoint. So let me just call this the transfer function of the equalizer versus frequency. Where again, what you're doing is you're trying to make the gain at DC lower than the gain at high frequencies. Now, let me ask you guys a question. If I was to go and just take some circuit, let's say your amplifier or something like that, and I was to modify it to have this shape, and by the way, we'll see exactly how we do that in 1 second. But if I was to take it and modify it to have this shape, who thinks that when you do that, you're actually going to get extra gain at high frequencies? In other words, that let's say you built your amplifier to have a gain of, 2 or 3 or whatever it is, and then you were going to make it so that magically, without spending any extra power or anything like that, this now became a gain of, let's say, 10 or 20 or something along those lines. Who thinks life works that way? Okay, good. Perhaps just by the tone of my question, life does not work that way. So what typically does actually happen? So if you're going to build something like this, by the way, and this is true either at the transmitter or at the receiver, what are you typically actually doing to implement a transfer function like this? Adding a zero. That is true. Bingo. what you typically are actually doing is taking something that would have given you this, meaning would have given you higher gain at all frequencies, and actually throwing away gain at low frequency. Okay, so again, this is unfortunately sort of a fact of life of just about any which way you can build this. There are a couple of exceptions that, if you're interested, come bug me, but they mostly involve building huge inductors all over the place, and, as we've said long time ago, that's typically not what you want to do in this particular context. So unfortunately, what you typically are really doing is taking gain, or rather signal swing you would have had at DC, and actually throwing it away. So what does that mean that you're actually doing in terms of, let's say, the signal-to-noise ratio when you actually include this kind of equalization? Given the fact that you're actually throwing away signal at DC, what has to be happening to the signal-to-noise ratio? I heard somebody say it. So who thinks the signal-to-noise ratio gets better? Stays the same? Worse? Okay, good. Gets worse, right? You have less signal. Noise basically didn't change, or perhaps maybe changes only a little bit. And so guess what? By doing this, fundamentally you're actually making your SNR worse. Now, having said that, you still end up having to do this, right? You still have to build this equalizer, because if you don't, the ISI basically kills you. But the point of saying this, and this is, by the way, maybe just a sort of side note, if you ever talk to the sort of communications folks, this effect of you having to basically have worse SNR by doing the equalization is what's known as noise enhancement in that community. It's really just a way of saying that if I didn't have something that was a really nice flat channel and I have to apply some kind of filtering to correct the channel, sorry, you're always going to make the noise worse than it otherwise would have been. So in our particular context, despite that fact, equalization still is actually a very, very useful thing to do. Because as you've probably seen even in your project already, you typically are not super noise dominated, at least not unless you have extremely low levels of power consumption. Right? You're usually dominated by just sort of how small of a transistor can you build, or how much load cap do you have to drive. That's usually what's kind of setting the power consumption in most of these links. And so because of that, you're totally happy to basically take some penalty on the noise just to be able to clean up all of the ISI that's in the system. Now, having said that, again, you can't take this too far, because eventually, indeed, in particular, let's say that you needed this to be down at, or let's say you needed this ratio to be something like, I don't know, 60 dB or even 40 dB or something like this. Now you're clearly throwing away a lot of your signal. Right? And so therefore, now you might really start hitting the condition where, okay, sorry, actually the noise matters quite a bit. But let's say the good and the bad news is that for most links, at least today, you're not dealing with things quite this bad. It's usually more in the range of 30-ish dB or so. And that's already a sort of pretty bad channel, so to speak. Does this make sense to everybody? Or? All right, so given that that's the case, let's think a little bit about how we would now actually build these equalizers. And as I said before, I'm really going to focus on the receiver, if nothing else because the impedance tends to be higher on the receiver. And so you can typically build these equalizers using less power on the receiver than you can on the transmitter, particularly in the analog domain. So the first thing I should mention is there's a bazillion different ways to build a transfer function that looks similar to what I drew a second ago. So I'm not going to claim that this is going to be an exhaustive walkthrough of all of the different types. But what I'm going to do is give you a little bit of a flavor as to what the sort of really typical way of doing, or the typical idea is behind most of these implementations, and give you a few ideas about sort of what are the key trade-offs or issues to be worried about. So it turns out that, especially in the receive analog side, almost all of these sort of, let's say, equalizers that people build actually end up being implemented by doing some kind of a feedback through a low-pass filter. Okay, so the idea is something like the following. let's just say you took your original front-end amplifier design that you had done, let's say either in phase 1 or in phase 2. And let's say that that amplifier, of course, had some transfer function A of S. If I then wanted to go and make this amplifier, rather than just being an amplifier, actually perform the function of equalization as well, well, the simplest way to actually do that is to just take the amplifier, essentially the same amplifier I had before, and then tie it into feedback through this so-called H of S. Or let me actually be a little bit careful. Let me call this G of S. All right, so mathematically, and let's just call this V out and V in, what would the transfer function of this new system be? Purely from a math standpoint. There we go. A of S over 1 plus A of S times G of S. And hopefully, as you guys all know very, very well, if A of S has high enough gain, then roughly speaking, the closed loop transfer function is G inverse of S. All right, so now given that that's the case, and that we really want to be building an equalizer out of this, what would you want G of S to actually be? Like, how would you want to, in some senses, let's say, quote unquote, implement it? Okay, it should have a low frequency pole, but let's actually be a little bit more precise. So in this picture here, what would be the ideal G of S for you to use? Yeah, H of S, capital H of S, right? So physically, how would you do that? Or what would that imply? Like literally, what does it imply to have that feedback be H of S? Yeah, it literally means you use the channel. Now, what's the minor, quote-unquote, practical difficulty with that? And just as a reminder, the channel is, I have a chip, it goes to a PCB, there's some trace on the PCB, there's another chip somewhere, packaging, etc. So what's the minor practical difficulty? Yeah, I can't make the channel inside of the chip, right? Because even if I tried to replicate the channel and I sort of copied the PCB or something like this, I'm not entirely sure how I make that, come out of my receiver and go back in and really actually be the same, right? Clearly you can't actually do that, right? What you instead have to do is somehow build something in that G of S that hopefully mimics the behavior of the channel. So the bad news is there's no way to really get the channel exactly right. The good news is you can usually build some fairly simple, essentially RC circuits that at least give you things that reasonably well match at least the simpler channels. So as an example, a lot of the channels look like they have maybe 1 or 2 sort of low frequency poles in them. Well, that means that this G of S essentially just needs 1 or 2 poles in it as well. And of course, we can build those by essentially RC circuits. So, by the way, what I'll mention now is, or what I'll just as a note now is, everything that I'm going to show you in a second is all going to be based off of just single pole filters in this G of S. In other words, it's going to be creating only 1 0 in the equalizer. So it's kind of like assuming that the channel itself is just a simple first-order low-pass filter. But you can actually make sort of everything that I'm showing, you can make it actually match these more complex channel shapes, either by literally adjusting this G of S, or by combining together a couple of the different techniques that I'll show you. And we'll see that in one more second. So, what I want to do now is, given this idea of I want to build this feedback-based equalizer, where essentially what I need is somehow to sort of take that low-pass filter kind of thing and feed it back, let's see how we can actually modify sort of a simple front-end amplifier to actually include exactly this kind of effect. So what I'll first do is just draw the original amplifier, and then we'll see if we can kind of figure out how you would modify it to actually include this equalization capability. Okay, so let's say that's the positive input, that's the negative input, and that's, let's say, my original amplifier there. And just for the sake of clarity, of course, it's always going to have some parasitic capacitance that it's going to have to be driving. Okay, so how am I going to take this thing and basically modify it to do something similar to that picture on the right there? What do I have to do? And again, let's just assume that our channel is just a first order low pass filter. What's the first thing you might want to do? Yeah? Okay. So you said you can do source degeneration with an R in parallel with a C on both sides. That's absolutely correct. That's slightly more sophisticated than what I want to do just now, but we're going to come back to that one. So that's absolutely correct. That's a great idea. I'll explain why it's such a great idea in 1 second, or maybe in a few more minutes. But to see why it's a great idea, we have to see sort of what the other versions of things are. So if I'm, let's say, pretty literally trying to follow this block diagram here, and to be honest, the source degenerated one actually does follow this fairly literally too, but what's another way of doing it? All right, let's start with the easy thing. How am I going to do G of S? How am I going to build a low-pass filter? With what? Okay. So you said you're going to put an RC filter, essentially. I'm not actually going to sort of, in this case, do it on these caps that I've shown here, although you could actually do that. I'm going to assume for a second that these caps are basically what I have to drive no matter what. Okay? But indeed, I could actually take these outputs and basically low-pass filter them with some kind of RC circuit. Okay, I could certainly do this. All right, so now what do I need to do to kind of complete the picture? How am I going to actually have this feedback and create the effect that I'm interested in? Yeah, exactly. I can just connect this to another differential pair. This is an example, that and this, and I believe I got the polarity of the feedback correct. All right, so in other words, what I'm basically doing is I'm going to take the output, pass it through this low-pass filter, and then just add it into this second differential pair that has some GM associated with it that will essentially create the negative feedback onto that output node. And again, just to be totally clear, my outputs would, of course, be taken from there. So I believe this is Vout minus, and this is Vout plus. Does this make sense to everybody? Or? So just to make sure it's sort of 100% clear as to why this behaves the way we want it to, let's think about the input impedance looking into this structure here. And so you guys tell me, and we'll just do a plot of this over here. So if we look at the magnitude of Z in versus frequency, and let's just say that this has GM1 and this has GM2. So if I look into this side right here, at DC, what's the input impedance? And by the way, don't worry about the resistor and the capacitor in terms of their impedance. Just assume that they behave as a perfect low-pass filter. Yeah, it's just 1 over GM2. Because after all, at low frequency, this low-pass filter is just a short, right? It's just like tying these transistors into a diode-connected configuration. So I just get 1 over GM2. Okay, well, so it's going to stay 1 over GM2. Now, at what frequency is the impedance going to start to change? And let's just label everything we need to label. Let's just call that CF, CF, RF. Yeah, exactly. This is just at whatever the RC time constant is. And now here's the interesting question. Does the impedance go up, go down? Yeah, it should actually go up. Because notice you're starting to actually not have as much of the output signal make it back to the gate of the transistor, which means it's applying less feedback. Or in other words, it's seeing a smaller signal at the GM there, which implies it has a higher impedance. So in other words, if you actually, at least ideally speaking, the impedance would do what I've shown there. Now, by the way, what other, let's say, purely passive circuit could you build that would have a similar looking impedance plot? Like, I just want to replace that whole structure that I drew there with some other circuit that will behave the same way from the standpoint of its impedance. Yeah, exactly. This is completely equivalent to a resistor in series with an inductor, right? Where that resistance would just be 1 over GM2, and the inductor here would basically be set by whatever equivalent inductance is needed to make the L over R the same as this, or the R over L to be precise in terms of frequency versus time constant. Okay, so notice by playing this trick, what I'm really doing is essentially building what's called an active inductor. And the way I do it, just like we had said originally, was I'm going to be using this GM stage here to create a low impedance at low frequency. But then at high frequency, I'm just going to make that GM effect go away. In other words, I'm going to let the gain go back to, or rather the impedance go back to whatever it would have been anyways. Now, by the way, just to be totally clear, this actually does not go off to infinity. Right? In reality, there's always going to be some output resistance either from the load structure or from the transistors themselves. So of course, in reality, what you actually end up with is, if I looked at just the impedance at that node that naturally would have existed, you're going to have something that, for example, looks like this. And so if we then look at the composite transfer function of the overall equalizer, it will, of course, look something like that. In other words, it will initially be dominated by that low impedance of the feedback structure. Then, once the feedback sort of starts going away, the impedance will go up. Eventually, you'll hit the maximum impedance you could have had anyways. And then you'll just sort of start to fall back off again with the load capacitance. Now, just one other sort of quick note. Depending upon where you place this, the picture may not look exactly as I've drawn there. So just as an example, if you were to say, do something like, I'll do it with, let's say, this color. If you were to do something like, for example, have the inductor curve look like this, right? Your overall equalizer shape would end up looking like this. Okay? So the thing to sort of be careful of there, or the thing to maybe pay attention to is, this may or may not, first of all, match with what the channel response you're actually interested in. Right? Because notice that basically, if I really had just a simple first-order low-pass channel, then what I really want is something that basically will just kind of go up and up and up. And then only once you really hit the maximum bandwidth, only then does it actually roll off. The reason this is kind of problematic is that you have to remember the way we got this shape in the first place was actually by throwing away gain at DC. So in other words, if I know that the ratio between the peak gain I wanted and the minimum gain I wanted was, let's say, a factor of 10, if you end up with a shape like this, that means that because you push this over to the left, right, if you still have that factor of 10 here, there's no way for you to necessarily place the pole exactly where you wanted it to be. Okay, this is maybe a little bit more of a subtle thing. If people are sort of interested, they can come and bug me later. But the take-home story or the take-home message there that hopefully should be clear is that you really have to be careful with where you place the sort of the poles and the zeros here. Because as we talked about before, you really want to put the 0 right where the pole of the channel actually is. And particularly for these kinds of implementations, that places sort of pretty stringent constraints on what the shape of this curve should really look like. And in particular, where both the 0 and the sort of final pole of the whole structure should really be. Okay, so this works. This lets us build an equalizer And by the way, just maybe as a side note, as I'd mentioned before, this whole structure here is really mimicking an RL circuit. The reason we don't actually end up building this RL circuit is that if you calculate how big the inductors would actually have to be for sort of the practical capacitors that you're driving, you'll see that they're often in the microfarads, if not even tens of microfarads range. In other words, way, way too big for anything that practically would be interested in on our IC, at least at the kind of data rates we're talking about in our project. So, again, looks good, it works, it's compact, and etc. What's maybe bad about this? What's the disadvantage of exactly building this equalizer this way? Yeah, okay, you said I'm burning twice the power. In fact, I might even be burning more than twice the power. Because depending upon what I want that DC gain value to be, right, I could actually even have to spend more power in the secondary GM thing than I did in the first GM thing. So really, to say it another way, I'm actually burning extra power just in order to throw away gain at DC. So that seems really wasteful, right? Because I have less gain and I'm burning more power. Which usually, if you have less gain, at least I should be able to not burn any more power for it, right? I should at least be able to burn the same power as I burned before. So that will actually bring us to a couple of the other, let's say, feedback-based variants, which conceptually at least are actually very much the same idea as what we just drew, but are a little bit more efficient in terms of actually implementing that type of equalization. And so the basic idea of both of the sort of versions that I'm going to draw now is actually to, rather than build this sort of feedback section here with another input pair, why don't we effectively just reuse the load structure we would have needed, effectively either these current sources or the load resistors, but just modify them to also create this kind of, RL type of impedance. So let me just draw one of the examples, and we'll hopefully see sort of how this works. Let me switch to a more reasonable color. So again, I'll take my input pair. I'll have some tail current source there. And now what I'm going to do is, instead of just having, for example, PMOS current sources, now what I'm actually going to do is put those PMOS transistors to act as that negative feedback structure. And in particular, the way you would do that is something like this. Okay? So the idea here is pretty straightforward. I have my input pair, right? That has a certain GM associated with it. Then at DC, again, this thing just looks like a diode-connected transistor. So just like we had with the previous picture, my DC gain was essentially GM1 over GM2. Well, same idea. It's just going to be the GM of the NMOS devices over the GM of these PMOS devices. The advantage of doing this is that now I'm really just reusing the same bias current. Right? I don't actually have to spend extra bias current just to implement this feedback kind of structure. Of course, as with before, because of this low-pass filter, at high frequencies, these two PMOS devices should basically just look like current sources. Right? In other words, you should just have the RO of those transistors in terms of whatever the impedance looking out there is, at least at very, very high frequencies where this low-pass filter has completely killed any feedback. Which, again, is just like we showed in the previous picture. So, very similar idea. Perhaps somewhat more efficient because now we're actually reusing the load currents. But the particular issue you tend to run into with this is that, first of all, we had to use these sort of PMOS transistors, and especially if you're shooting for very, very high speed kind of things, the PMOS devices, if they have lower mobility, tend to add a lot of extra capacitance, A. And B, you have to be sort of careful about the DC headroom here. Right? Because basically you have to have essentially a full VGS across here, and these two VDSs across there. Not to say you can't do it, but if you're at very, very low voltages, it may or may not fit into your overall power supply. So there's another version of this, which actually at first when people look at it looks very, very funny, but at least gets around one of the issues, which is at least it'll use only NMOS transistors. So the way we can do that is the following. So I'm again going to have my input pair. Okay? And now for my loads. As I said before, I really want to use NMOS transistors and not PMOS transistors. So now here's where things start to look really funny, right? Because usually you don't like sort of using NMOS devices as pull-up devices, right? Well, okay, but just bear with me. So the way I'm going to make this act like the equalizer is actually just by sort of adding those resistors in that I showed you there. Now, the thing you have to keep in mind is that there's actually always some capacitance from the gate to the source like this as well. So let's again see if we can sort of figure out how this thing might do what we want it to do. So just like before, let's assume that the input pair gives us GM1 and that these things on the top give us GM2. Well, these top guys here, they kind of just look like source followers, right? Or at least I should say maybe common gate input devices. Right, so essentially I'm just at least at low frequency, when I'm just putting VDD on the gates here, if I look up into those transistors, I just see a 1 over GM, right? Just like any other source follower. So just like with this structure and the structure before it, at DC, my gain would just be GM1 over GM2. Now the trick here as to why it actually causes the equalization is that notice, because of this capacitance here, once you actually start getting signal flowing through that cap, so that the VGS of these transistors basically does not change anymore as the source actually moves, once again, you're effectively taking away the feedback. In other words, if this cap was really a short, then for all intents and purposes, when you look up into that transistor there, it looks like an open circuit, right? Or at least it looks like maybe like an RO. Because now, there's no voltage signal across the VGS anymore. So of course the GM goes away, and just like in this picture, at high frequencies, basically the impedance actually becomes higher. Yeah, question? Oh, no. Oh, okay. Does this make sense to everybody, or? So again, the advantage of this particular configuration is that now I can actually use NMOS transistors throughout the whole structure, which, as we said before, potentially is less parasitic capacitance than the PMOS transistors. In terms of DC biasing, unfortunately, it's not really any better, because obviously I still need a full VGS across those NMOS devices to actually get them work with the V star that I'm interested in. And in particular here, you can see because the bias currents are the same, the only way you can really control GM1 over GM2 is by playing with the V stars of these two devices. Is this clear to everybody, or? Okay, so the final, let's say, example of actually building these equalizers, which in many ways actually does map to that original picture we drew, is a so-called source degenerated equalizer. And it turns out that this is by far the most popular, for reasons that people are only sort of recently starting to realize why it's actually so effective. So the way we're going to do this is something like the following. So let's say we take our input pair, and particularly in the differential case, I'm going to do something that initially looks a little bit funny. So I'm actually going to split the sources of those two transistors to be independent of each other. And out at the load over here, I'm just going to put load resistors, RL. So the idea here is the following. If I then go and add in an RE and a capacitance CE, and of course, let me just label the inputs. This is VI plus, VI minus. Then if you actually walk through sort of what's happening here, you'll find that you actually get exactly the block diagram we drew here. Right? Because remember, from the standpoint of this source here, this transistor kind of looks like a source follower, right? So basically, when the input voltage comes in and wiggles here, some fraction of that input voltage will also show up at the source right there. And depending upon what the impedance is relative to the 1 over GM, that will change how large of a fraction of the input actually shows up on the source, and therefore how much gain you actually get out of this structure. So maybe just to put this another way, and since maybe you talked about it this way in EE 140, this whole thing is just, sort of a classic, let's say, source degenerated thing, at least at DC. So if I wanted to know what the effective GM was at DC, what would that be? And let's assume that I know what the GM of the input devices is. Let's just call that GM1. So what's like the effective GM of that structure? Yeah, exactly. It's just GM1 over 1 plus GM1 times RE. And we have to be a little bit careful. There we go, RE over 2. Okay, because notice I've tied this whole thing up in a differential circuit. If you do the half circuit, you just get RE over 2. Okay, so indeed, this would be the effective GM at DC. All right, well, at high frequency, or in fact, let's say at infinite frequency, what is the effective GM? Well, no, I'm asking about the GM. The GM actually does not change. So my question is precise. Yeah, it's just GM, okay? Because, of course, at infinite frequency, what's happening is that cap just looks like a short. And if that capacitor is a short, then the whole thing just looks like a normal differential pair, right? No different than any other differential pair. So notice, just like with all of the other ones, what we were really doing was, by adding in this source degeneration, we're making it so that at DC, we have less gain. In this particular instance, we got less gain by reducing the GM. And at high frequencies, we got more gain, or rather, we got our gain back. Right? In other words, we got the full GM coming out of it. Now, I'll mention a couple of things that you have to be careful of here in terms of really building this. The first is that, although this looks quite simple, there's a couple of things you have to remember. One is that, unfortunately, there's always an RO on those input devices. And what that means is that, unfortunately, there's going to be some link between the impedance out on the drain side and the impedance on the source side, which means that the actual transfer function you get will somehow have interactions between how you choose RE and how you choose RL. That kind of gets to be annoying because when you do the design, you really don't want to have to worry about that interaction. You'd really just want to be able to say, hey, look, I'm going to put an RL here to drive whatever load cap I want to be driving. And I'm going to put the RE and CE here to really just create the transfer function that I'm interested in. So the typical way that you end up solving that, or at least addressing it, is you probably will not just have a single input pair like this, but you'll actually add in the cascodes. Not because you really need high gain out of the structure, but only just to give you isolation from the load side of it. In other words, just to make it much easier to really do the design. The other thing I'll sort of briefly mention here is that notice there is one big advantage of this, which is that headroom-wise, I actually don't have any extra VGSs, A. And B, I really can use a resistive load here. Right? I don't need any extra active devices to create the filtering shape that I'm interested in. So from a speed or parasitic standpoint, this is also quite attractive. The final thing that I do want to briefly mention here, which again is somewhat of a subtle point, but actually turns out to be very, very critical, is that notice the way I create my high-pass filtering effect here is actually by modulating the GM. Whereas in all of these previous examples, the way I did it was actually by modulating the load impedance. So now let me ask you guys, and I guess maybe the answer to this will be somewhat obvious, but I'll tease out why it's the case. If you had to choose one method for implementing this high-pass filter, which method do you think is more effective, especially in the context of your project where I told you as an example that you have a 4-PAM signal and that signal can vary anything in terms of its absolute swing by a factor of 5. Which one do you think is actually more effective in terms of implementing this equalization function? Reducing the GM and then bringing it back at high frequency, or reducing the load impedance and then bringing it back at high frequency? Yeah? Bingo. Okay? So it turns out this is really the way you want to do it. You really want to be playing with the GM. And the reason for that is the linearity. Okay? So notice, and maybe we can do this on this next slide here. And I'll just draw the sort of input pair in the generation. Don't worry about the sort of load side for now. And actually, let me even draw it sort of as a single-ended thing just to make it easier. So this is kind of my equivalent single-ended circuit. Well, notice at DC, this whole thing just becomes a source-degenerated amplifier stage. Well, what's really nice about source degeneration is that if I put in pretty big signals into Vin, right, in some sense I just have a feedback loop here, right? Where that feedback loop is just trying to make Vin track on the source node there. Or to say it really another way, the effective sort of transconductance of this thing really just becomes something like 1 over Re, where this is the Re here. And Re, of course, is very linear, right? It's just a resistor. So to say this maybe in a slightly different way, remember we said that with any sort of differential pair, we would tend to get something like, if we looked at delta I over delta V, we would get something that looks like this. Well, by doing this source degeneration like this, we're basically bending this whole curve over, right? Because we're actually reducing the GM to push us out like this. That's actually really, really beneficial here. Because remember, the whole trick was that what the channel actually does to us is that it likes to pass low frequencies, but it doesn't like to pass high frequencies. So if I'm going to build this equalizer on the receiver, that means that what the receiver is going to see is big signals at low frequency and small signals at high frequency. And again, if you have something like a 4PAM system and gain variations and etc., that means you can very easily get very, very big signals up at DC, and at the very same time, get, unfortunately, small signals at high frequency. Well, the real beauty of this is it basically says, well, okay, fine. If you're going to give me big signals at DC, I'm source degenerated. I have a much wider linear range. And then if you give me small signals at high frequency, well, I know those signals are small. So in other words, they'll always sort of fit inside of this range here. So hey, there's no reason why I can't actually have higher gain for those high frequency signals. Does this kind of make sense to people, or? So in other words, the real critical point here is that the beauty of this source-degenerated type of topology is not only does it very naturally give you the types of transfer function you're interested in, it also has exactly the sort of dynamic linearity that you're interested in. Because again, it gives you very good linearity at low frequency where the signals are big, meaning it gives you're allowed to actually put those big signals in and not compress anything or not have anything clip out. But at the same time, you can actually get the high frequency when you know the high gain, when you know that the signals will be small at high frequencies. Any questions on this, or? Okay, so if there's no other questions, that's really sort of what I wanted to cover for today, and actually, of course, for the whole class. So really, just as a reminder, we walked through quite a bit of material now, all the way from obviously modeling transistors, understanding sort of what the sort of simple design approaches might be, particularly using the V-star to kind of abstract away a lot of the technology details, to then really looking at how we would use that in specific amplifiers, common mode, feedback, and things of that nature. And then now starting to look at these more complex systems and trying to understand how we use these basic sort of analog design ideas to really then figure out the design trade-offs of each of the individual blocks inside of this system. So I'll just give you sort of the final reminder that I started the class out with, which was my hope or my goal with this class was to make it so that, in the future, if you go out and you're working on some large analog system and somebody says, well, here's your spec for this block, you should immediately say, no, I'm not going to build that. Tell me why you need it, because if I change it this way or that way and you do something else over here, I can actually get a better result. So that's indeed, the sort of the techniques that you need to think about that, to think about how you'd really do that optimization is exactly what I hope you guys have sort of picked up through the course of the class. So with that, it's been a pleasure giving you guys all the lectures, and you're not quite done yet, so you'll still be seeing me on Monday and, of course, on Wednesday after that. But other than that, I hope you guys are doing well in the project, and good luck. And we have the HKN things now that I guess Samit's going to hand out.